All right. So now we are going to talk about the strain. And strain is a very important quantity for ferroelectrics for many reasons. One, of course, is that one very, not completely unique, but certainly very characteristic feature of ferroelectrics is that they are piezoelectric. And if we want to describe piezoelectricity, we have to necessarily include a strain in our discussions. Another aspect is that many ferroelectrics are extremely sensitive to stress, extremely sensitive to variations of strain. Okay? You can really tune the behavior massively by, for example, growing them in thin films where you control the in-plane lattice parameter. And that is essentially a reflection of how sensitive they are to a strain. Okay? So having a strain explicitly in the models or in the discussions is mandatory in many cases. But beyond that, a strain also gives us an opportunity to complexify, so to speak, our discussion in a non-trivial way. So we started with a very simple theory for a discontinuous phase transition, and then we saw how we could make, for a continuous phase transition, and then we saw how we could generalize that one to make it discontinuous. We saw how to compute response properties to small fields from that theory. Then we have seen how to compute response properties to large fields from that theory. And now we are going to go in a completely different branch. We are going to see how we can extend that theory to include an additional order parameter. So by doing this, once you know how to do it for a couple of order parameters, pretty much you are equipped to do it for anything that crosses your way in the future. Okay, so a strain. First of all, let us give a definition. So we are going to go back to our model crystal, where that circle in the middle is a positively charged ion, so a cation. And you remember that we define polarization essentially as the off-centering, a way to quantify the off-centering of that cation. And now we also have to define a strain. We are going to do it all in one direction for simplicity. So let's imagine that at equilibrium in the high symmetry structure, this crystal has a lattice constant. We call it A. Let me call it A0. It means reference. It means no perturbation, etc. But in general, we want to allow this lattice constant to fluctuate, to vary, to take any value actually, although we are going to take A0 as the reference. Okay, so for example, we could imagine that we have a situation like this. I am always going to exaggerate a little bit, with this atom still in the center. And so this configuration has obviously a different lattice constant A. And what we are going to do is to measure this A with respect to A0. Okay? So essentially we are going to write A as A0, 1 plus a new quantity, which is what we call a strain. Okay? A strain is introduced in a different way in textbooks, but ultimately when it comes to homogeneous strains that that would describe how the whole system has elongated in this way, so every unit cell is now longer along the vertical in that way, this is a sufficient definition. So in this state, eta is 0, okay? And in this state that I have drawn here, eta is positive. Okay, so a positive strain typically means that we are stretching, we are elongating the material along a particular direction. We are elongating the lattice vector. All right. Now, let me, for the purpose of the discussion and to introduce what a strain can do to a ferroelectric, let me draw a situation with negative strain, right? I'm going to exaggerate again. So this is 0, positive. Let me draw here negative. So here we have yet another value of A. and this obviously corresponds to a negative strain. All right, negative strain. So I'm drawing this exaggerated case just to make a point, which already tells us that indeed a strain must interact with ferroelectricity somehow. Because if you remember, we hypothesize, but this is not a crazy hypothesis, this is very much what happens in many systems, that the ferroelectric distortion in this crystal could be related with the fact that this atom wants to go out of the center to form bonds of a certain length with those two anions, those two oxygens in our simplified picture, right? So if that happens, we go to a state with positive polarization, right? And of course, there is a state with negative polarization that is exactly equivalent to that one, where the atom moves down. But the whole point is that we were hypothesizing that the physical, or if you want, chemical driving force for this to happen, and therefore for ferroelectricity to occur, is that this atom wants to have a preferred bonding distance with those neighbors. Okay? Fine. Now, if we are in this situation or this situation, we could ask exactly that question. Okay, with this in mind, if the central atom wants to form relatively short bonds, will that tendency or will the necessity, the need to go off center become stronger when we do this, or maybe when we do this, or what? And this question actually is difficult to answer in general, but here in this limit, it lends itself to a very clear intuition, right? If I apply a negative strain that is really massive, so that when the atom is in the center, it already satisfies, or it's already having very short distances with the neighbors, then in this situation, this atom doesn't need to go off center at all. And if it doesn't need to go outside the center of the cell, then it doesn't need to break symmetry, and it will not give us any polarization, it will not give us any electric dipole, no phase transition, no ferroelectricity. Okay? So compression like this, and actually this is very much observed, certainly in ferroelectric perovskite oxide, for example, compression typically kills ferroelectricity. Okay? And we are going to see it mathematically in a second. That limit is pretty clear. Essentially, there is no room for this atom to go out. You can also think about it in that way. And then to first approximation, we will see it mathematically in a moment, this guy probably will favor ferroelectricity. So if the atom is really very far, the need that it feels to, or the energy gain by going out becomes even greater as compared to being there in the center, disconnected from everything else, because it wants to form bonds. Here, the bonds are not optimal when it is in the center, but maybe there is some bonding because it's still close. But here is far, the bonds are broken, so that's certainly not optimal, and it really will want to go out. So negative strain kills the ferroelectric instability, kills polarization probably. Positive strain probably will favor the ferroelectric instability. Okay? This, as I said, is very much observed in many materials. All right, so now let's try, with only these very, very simple intuitions, let's try to work out a theory that allows us to put all this in mathematical form and see if we recover our intuitions, but and more. And we can predict more based on that theory. So let me remove this one. So what do we need to do? Let's hypothesize that at the level of the ferroelectricity, imagine for a second, we could imagine that we deal with the system always at eta equal to 0. This is what we were already doing before. Eta equal to 0, the atom wants to go out. This will eventually lead to some sort of ferroelectric phase transition because at high temperatures it will get disordered. At low temperatures, it really breaks the symmetry. Okay, and we saw that we could write a Landau theory of this form to describe all that. Okay, in this Landau theory, the variables are p, and we have a external control parameter that is the temperature, and of course we can put an electric field also. Okay, now essentially what we want to do is to have a theory that also describes a strain. Right? And in the spirit of starting as simple as possible and then adding complexity in a systematic way, we are going to continue thinking about polynomial expansion around a reference, which I am already introducing here implicitly, right? The reference state is the state with eta equal to 0, with p equal to 0, etc., etc. Okay? And as we emphasized in the previous lessons, we are not so concerned about being in the perturbative regime, but this still is a good way to think because it imposes all the symmetries naturally, and it allows us to introduce complexity in an ordered manner. Strain. So what do we know about the strain? So we want to study the energetics of this system as a function of a strain. Well, there are two parts here, right? We could imagine thinking about the term that we have a strain alone. So we strain the system, but we do not create a polarization like here. The polarization of these guys is still 0, but the strain is positive, right? Okay. And eventually we want to see how the strain and the polarization couple together. That's what we need to do. So let's start with the strain alone. So let me write here f of eta. It may depend on the temperature, but well, actually that's an interesting consideration. In this very simple approach, we are going to assume that the strain by itself, it doesn't do anything. The system doesn't want to generate a spontaneous strain by itself, okay? It's boring in that sense. The most that can happen is that you have thermal expansion. This means that in these terms that I'm going to write here, in principle, I don't need to worry about the temperature dependence of the parameters, okay? Let's assume that is the case. And by the way, this tends to be the case in the vast majority of materials of interest. Okay, so coming back to, there is no temperature here. That's what it means. But coming back to this, I would have a term that depends on the strain and a term that depends on the interaction between strain and polarization. All right, that's simple enough. So let's start with this one, which probably is easier. Okay. If we want to write the energy of this system as I strain it, it stands to reason that in principle, I can have a linear dependence of the energy, and then a quadratic dependence of the energy, and then a third order dependence of the energy, etc., right? So in principle, I could have here a parameter multiplying eta, and b a parameter multiplying eta squared, c multiplying eta to the third, dot dot dot. Okay? And we want, of course, to use the simplest possible theory, but which is also physically acceptable and sound. So the first thing that we have to worry about is whether these strains, if you remember for the polarization, we convinced ourselves very quickly that we could not have odd terms in the polarization. So p and minus p states have the same energy, meaning that if I move this atom up or down, the energy has to be the same. What happens with the strain? With the strain, stretching as there, the question that we need to ask is whether stretching like that is the same as compressing like this, right? So here I have positive strain, here I have negative strain. Do these two things have the same energy? And the answer is obviously no. These two situations are not related by symmetry in any way. In one of them, if you want, the distances between atoms these distances are large, and the other one, they are small. There is no symmetry that is going to change the distances between atoms, no symmetry operation. So these two are definitely two different strain states. So it clearly means that having a positive strain has to cause an energy change that is different from having a negative strain. Okay? So this term, so the terms that are linear, or the terms that are odd in the strain, are in principle allowed by symmetry. There is no reason to remove them. All right. What about the terms that are quadratic? Well, since we said that the positive strain and negative strain are essentially unrelated, we also don't have any expectation for these terms to be zero. So the energy dependence with respect to a strain, as we make positive or negative, is totally general, and in principle, all terms are allowed by symmetry. Okay. This may sound a bit more shocking because we have made arguments for things to be zero, not for things to be different from zero. But in principle, you know, this stuff can be different from zero. In fact, in most materials out there, when you plot the energy as a function of lattice constant, you will see that they have behaviors like this. So there is a minimum for the equilibrium lattice constant, and then the energy disperses quadratically. It's approximate, it's not perfect, because this would be our minimum would be our A0, and then around it, we have to have a linear term. It's not the same thing to expand as it is to contract, but certainly we see something that looks like a parabola all the time, right? We typically see things like look like this, that are telling you that actually expanding typically takes less energy than contracting. Contracting beyond some limit forces you to put the atoms together, and that's very bad. Expanding at some limited, in some limit, it says that you are breaking bonds. That's hard, but it's doable. It happens all the time. Okay, but clearly there is a quadratic term, no question about it. So that can be different from zero. Okay. So in principle, all the terms can be different from zero. So we have to retain them all, or at least a few of them to make a simple theory, but in principle, they can be different from zero. Now, in practice, something interesting happens, right? So, as I said and emphasize, by symmetry, there is no reason why this linear term has to be zero. But in practice, when we describe these situations, it's always possible to put ourselves to choose a reference, to choose A0, so that we are at a minimum of the energy. So in practice, we are free to choose a reference such that we start from a minimum. And if we start from a minimum, essentially we are saying by definition that the first derivative, which is this guy, evaluated at the minimum, is zero. Okay? So this is not symmetry, it's choice. So chosen to be zero. Okay? And we can pretty much always do this. There are some subtleties as to how you would describe, how would you handle thermal expansion in a theory like this. Thermal expansion would give you a term that essentially is like an effective pressure and is linear in the strain, but that's too much for today. Okay. So this means, and this is what we are going to do here, we are going to assume that from the point of view of a strain, our eta equal to zero state is one in which you don't feel a stress to make eta different from zero. Because if we have this term, it would literally mean that for zero polarization, the system is already under stress, taking it to a different value of strain. Okay, so we prefer to start from the minimum. Sounds good? All right. So with that simplifying assumption, we can already give a form to this. We are going to give it a quadratic form. We would have a third order term, etc. By putting ourselves in a minimum, we are not making this one zero, obviously. But we are going to stay quadratic for simplicity. And in fact, now let me change a little bit the notation, because the form we are going to give to our free energy as a function of strain, we are going to give it that form. We are going to call our quadratic term C, which is the way that you usually find the elastic constant in your system. Okay, so this is the basic. Interesting what happens with the yellow. It's only it's only with the blue ink. A little experiment. It's only with the blue. Anyway, okay. So let me draw it. No, so let me write it there already. It's very small, and in this way we make room. 1/2 C eta squared. All right. Quite trivial. I didn't say it. Let me say it now. Normally, this C parameter will be positive. Okay, so C will be a positive constant. That says that I am always, from the point of view of a strain, everything is trivial. I am living at a minimum. That's it. By itself, a strain cannot do anything. I am living at a minimum. All right, and now let's go with the interaction term, which is obviously the most interesting one. So in principle, following the usual approach, we could write here, in increasing order of complexity, the possible terms of interaction that we can have between strain and polarization. So we could have something, let me give them, now I'm going to use Greek letters. We could have something that is eta p, so linear in both strain and polarization. We could have something, let me call that one gamma 1. Gamma 2 would be eta p squared. Gamma 3 would be eta squared p. Gamma 4 would be eta squared p squared, etc. All right. And the idea here, of course, is to see if we can use symmetry arguments to get rid of some of this, or to find some underlying rules and identify the simplest coupling that definitely needs to be retained in a theory. Okay. So for the strain, we saw already, we are always using essentially only one symmetry, which is kind of a mirror plane with respect to this position, right? So this mirror plane brings this atom from up to down, so it changes the sign of polarization. And by application of this mirror plane, the energy of the system should not change. So we are not going to do anything more sophisticated than that. Okay? Okay, if we take this state, for example, by the way, where the polarization is 0 and the strain is positive, and we use that mirror plane, these two atoms will come here, and these two atoms will go there, and we have a state with exactly the same strain. So these symmetries, point symmetries, don't change the volume of your unit cell, let's say, put very directly, so naturally they don't change the strain. Certainly not this strain. We could have a symmetry that changes this strain from the vertical to the horizontal if I rotate the whole thing. Okay? But the volume of the unit cell doesn't change. In our simple case, a strain is invariant under these mirror planes. Okay? But now we can ask ourselves the following question. Imagine I fix the strain to positive, okay, just to say something, but I move this atom up. So I have a state with P positive. Now I apply this mirror plane that I know I want to have respected in the expression for my energy, and this atom up goes to atom down with P negative. Okay, so here we have two states. Strain is positive, it hasn't changed, it's the same in both, but in one of them the polarization is positive and the other one the polarization is negative. These two states are clearly equivalent. We have constructed them, we have constructed the second by using a symmetry that is lost when the polarization becomes different from 0. So they are warranted to be equivalent, but it's intuitive enough that they are equivalent, right? So they have to have the same energy. But what has happened? Strain has remained the same, polarization has changed sign. So if these two guys have to have the same energy, it means that in general, for the interaction term, it has to be true that F interaction of P and eta has to be equal to F interaction of minus P and eta. Okay? So the energy of our system, the full energy, still has to be even against changes of sign in the polarization. And if that has to happen, all the individual terms of the energy have to satisfy this, including the interaction term. All right? But if this is the case, then by symmetry, we already know that this Poisson parameter has to be 0, because here I have a term that is linear in the polarization. That will violate this condition if it were to be different from 0. And this gamma 3 also has to be 0. Right? So actually, in a sense, we already have an answer, apparently, to our question, because our system essentially has one symmetry that we want respected, and that symmetry is compatible with having this kind of coupling. Again, our symmetries are going to change P to minus P, or leave it invariant, so P squared will always be invariant, and our symmetries leave eta invariant, the symmetries that we want to see respected. So this term is fine. Whatever we do to the system, change the sign of P, eta cannot change. The combination eta times P squared continues to have the same value. So it contributes in the same way to the energy. So it's perfectly okay. You could say the same thing about this term, by the way. So anything we do, eta will be the same. Polarization at most changes sign. So eta squared P squared will not change. So this is an invariant. This is perfectly allowed by symmetry. But here, for the sake of simplicity, we are going to stay only with the lowest order coupling, which is linear in the strain and quadratic in the polarization. Okay? Simply, this is the simplest coupling. It's always there. You see that this argument is absolutely general. You are going to have a coupling like this in every system, in every ferroelectric. And we are going to see what this coupling gives us. All right? So let me write it here. Our interaction term in this very simple theory is going to have the form gamma eta P squared. Okay? There could be more things like this eta squared P squared, but certainly we cannot have something like linear in eta and linear in P. This is not allowed by symmetry. This is the simplest term that we can find. Let me make a bit of room. All right. Very good. So now we have our simplest theory of ferroelectric, not only with polarization, but also with strain. We have already seen that, by the way, this parameter C is positive. Okay. Do we know anything about the sign of this parameter gamma? We know it can be different from 0. At least symmetry doesn't have any problem with that. Do we know anything? Actually, we do. I have just argued, in order to convince you that the strain can affect the polarization, I have argued that when we compress, so for negative strain, the polarization really suffers. It could even be that because this atom cannot move any longer, it doesn't have a space, we don't get any polarization at all. Okay? In order to capture that mathematically, and conversely, when we have a positive strain, this atom probably has a stronger tendency to go out. To capture that mathematically, actually, the simplest way, it must be, that we have is to figure out whether this term can tell us something about that, right? And it can. So here we are saying that if eta is positive, for example, creating a polarization will result in a further reduction of the energy. So it means that if I make eta positive here, and if I make P different from 0, I would like to see the interaction between these two be such that the energy goes down. So we stabilize those situations. And for that to happen, because eta is positive and P squared is positive, then gamma has to be negative. Conversely, if eta is negative, and if I had a non-zero polarization, the idea that a compression will make polarization more difficult to happen means that if eta is negative and I insist in making my polarization different from 0, the energy has to go up due to the interaction. Okay, and that I also get by getting gamma negative. Okay? So this term that symmetry tells us, look, this is the simplest thing you can work on with. This term already gives us a mechanism to capture this basic behavior that, as you see, we can expect from simple arguments of, well, do the atoms have room to move? Okay. So surprisingly powerful stuff. And now, to finish this part, eventually we will use all this machinery to see if we can figure out the piezoelectric response. But to finish this part, let me ask the following question. And following exactly with this line of thought. Okay, now I have a theory that tells me how the strain couples with the polarization. I have also argued that if I compress enough, so for negative enough strain, the ferroelectric instability may well disappear. So I can ask the question, how much strain does my theory tell me that I need in order to do that? So for a second, let's imagine that the strain is a controllable parameter from the outside, okay? A controllable parameter from the outside. Then for this full theory, I can compute the equation of state for the polarization. Now strain is an external parameter, okay? Let me just intellectually think that my free energy is a function of the polarization and a function of two external parameters or external control knobs, if you want, the temperature and the strain. Okay, so you see I have put a strain on the other side of the semicolon. Okay? Let me imagine I can fix this from the outside, which I can, by the way, in many materials by growing my ferroelectric on a particular substrate, which imposes the strain effectively in a thin film. If I adopt this viewpoint, then it's very interesting. So if the strain is external, the energy associated to the strain alone is irrelevant. It's something that I am paying from the outside. I am straining my material that costs energy, but I can do it. Okay, let's imagine I can do it. So I can forget about that energy. Let me put it here. This becomes some sort of a constant. But then if I look at the rest, what do I have? I have my usual quadratic energy for the polarization. But then to that usual quadratic energy, I have an extra contribution coming from here. Eta now is a parameter, and this term goes as P squared. So I can bring it in here and write 2 times gamma eta. Ugh. 2 times gamma eta. P squared plus 1 to the 4. Okay? So you see, if I am able to fix a strain from the outside, my polarization lives in a free energy potential where the quadratic part now has a different form. But essentially, we also know from all the analysis that we have done before that in this very simple potential, the temperature, the Curie temperature, is determined by the temperature at which this term here becomes 0. So it's the temperature at which I don't have a minimum anymore at P equal to 0, and the minima correspond to situations with finite polarization. So I can ask the question, what is the temperature I need for this guy to become 0, right? So I can call that one, this is not good. Let's try the black, why not the black? Let me call that one Tc prime. It's a modified Curie point. So when this expression in the square brackets is 0, that corresponds to the strain. No, sorry. This is the temperature for a given strain. Okay. When I have a strain, this is the new transition temperature. Okay. And what is this Tc prime? This Tc prime is alpha prime. No, is Tc. Is Tc. So I can take that there. Plus. What am I doing? Tc. No, minus. 2 times. Am I doing this right? Yeah, I'm doing this right. Huh? So you see, under strain, I have a modified transition temperature. Does it fit our expectations? Remember, from our argument about the physical significance of the physical nature of the strain polarization coupling, we had deduced that this coupling constant has to be negative. Okay, so gamma is negative. Just for emphasis, let me write it like this. Let me put here absolute value of gamma and put here a plus. Okay, just to make it easier to see. So this means that when I compress, if I make eta negative, then of course this is negative contribution and I get a modified Tc that is smaller than my original Tc. Is that clear? For compression. Compression means eta negative, so this becomes a minus sign and my Tc becomes smaller than the original Tc. And in particular, I can ask the question, okay, how large does eta need to be so that the modified Tc is 0? So when do I lose the instability? When do I lose ferroelectricity? I lose it when my predicted Curie point is 0 Kelvin. Normally I have a Curie point at a finite positive temperature, obviously. But if I compress, I make this Curie point go lower in temperature, and eventually, once I reach 0, the ferroelectricity is gone. So for this, let me call then, this will be a critical, another C. Let me call this guy eta star. So when eta star equals minus Tc multiplied by alpha prime divided by 2 gamma, if I am able to apply a strain as large as this and negative, eta star equals to minus, and everything here is a positive number, right? Tc is positive, alpha prime is positive, absolute value of gamma is positive. So if I am able to apply this much compressive strain, I remove the polarization completely. Does this expression make sense? It does, because look, if Tc is very high, if Tc is very large, I will need to get a very large, in magnitude, negative strain. So the higher Tc, so the stronger our ferroelectricity to begin with, the bigger the strain or the compression I need to apply. Okay, so that makes good sense. It also makes sense that the stronger the coupling, so the bigger gamma, if the coupling between the strain and polarization is very large, if this gamma is very large in magnitude, then the strain I need to apply is very small, because very little strain already will have a very big impact. Okay, so it makes sense. And this, you could say, well, does this happen? Yes, it happens. In many ferroelectrics, it is observed that under hydrostatic pressure, which is the closest thing that we can find in a 3D system to what we are discussing, there is a pressure beyond which the ferroelectric phase is gone in the phase diagram. And that would correspond to a situation where the transition, the Curie point, has moved to negative temperatures, which of course are not so easy to access. Okay. So super important control knot for our ferroelectrics, and a very, very simple theory already captures something as interesting as the possibility of to remove ferroelectricity altogether, also to increase it if the strain is positive, also to enhance it by controlling the strain state of the system. All right.